الجزائر.
ان شاء الله يا رب ان شاء الله. ودروك وين راك؟
أنا غبي أغيار. يعني أنا راني في
الرياض.
رياض صافي 23 زون ولا 24 والله ماني عاقل، حتى الدنيا تجري مانيش عاقل قداش.
الله يبارك. الله
عمر.
يبارك غير البارحة.
والله غير أنا كي جيت على عام راني في 24.
الله
كنا
يبارك.
نديروا عام ومن بعد نشوفوا نروحوا. ربي.
فينالمون عجباتك بارابور لوروب؟
آه، شفتوا بكري على درك سان ريان افوار.
ياك.
نو نو درك راهي
Ça
راه مع
change.
الاوروبيان. الاوروبيان درك سي تو سكو تو فو كاين. وقت اللي جيت انا كانت الدنيا صعيبه شويه مي بون.
واي. أيوة، الحمد لله. غادي
Ouais.
نبارطاجي l'écran وقول لي فايز اسكو سي بون.
Mhm.
سي بون.
Je vais peut-être faire ça. هكا toujours le plein écran ياك راك تشوفه.
بون.
Oui.
اي تري بيان، ايوا على بركة الله.
واسمه الريكوردينغ بديت ولا مازال فايز؟
رانا ديجا اون لايف في يوتيوب. cette fois-ci درتها ديريكت في يوتيوب. Ouais.
اون تايم شارب ولا؟
On donne واحد 2 3 minutes de temps le temps que الناس يبداو يجوا. Oh. عندك البيو. Oui. Je l'ai partagé juste pour
عندي.
présenter. Ouais. Ouais, donc c'est bon. Donc on attend un petit peu le temps que tout le monde soit là. On commence. Hmm. I guess we can start, Masoud.
اوكي. بسم الله الرحمن الرحيم والصلاة والسلام على رسول الله وبعد. السلام عليكم جميعا. باسم ال ASCA Algerian Scholars and Competence Abroad نستضيف للمرة الثالثة تواليا بروفيسور نجيب لازار من جامعة مونبلييه. So first we start with the brief bio of Professor Najib, our speaker. Najib Lazaar successfully defended his HDR, thèse d'habilitation dirigée les recherches, at the University of Montpellier on November 18, 2022. He earned an engineer's degree in computer science from University Sania, Doron, Algeria in 2007. He obtained his master's and PhD degrees in computer science from the University of Rennes 1, France, in 2008 and 2011 respectively. He then worked as an INRIA postdoctoral researcher until September 2012 at INRIA Microsoft. From 2012 to 2013, he contributed as a postdoctoral researcher on the European Icon project in Montpellier, France. Since 2013, Najib has held an assistant professor position at the University of Montpellier and co-heads the Coconut team at the LIRMM lab. In 2019-2020, he was seconded to CNRS for a year. Najib's research spans constraint programming, data mining, machine learning, and software engineering with a focus on constraint acquisition, declarative data mining, constraint-based software testing, and artificial intelligence for neurosymbolic and trustworthy AI systems. He collaborates with Similar Research Lab Oslo on constraint acquisition for autonomous vehicles, with CEA Paris-Saclay Artificial Intelligence for verification, and NEHS Digital Artificial Intelligence for health. Our speaker, Professor Najib, he started a series of webinars on 20th April. The first one was on 20th April, the second one on 4th May, and inshallah, he will close the series of webinars today with the third and last webinar with the title. Let me read the title: Unveiling Insights, Constraints in Data Mining for Enhanced Pattern. Please, Professor Najib, go ahead and good luck, inshallah.
Assalamu alaikum. Thank you very much, Professor Misal. I'm really happy to be with you today for the third part of the series of webinars. Our first webinar at that time talked about the AI in general and the make a focus on constraint programming. Just a quick recall on that topic, where in artificial intelligence we have this part of knowledge representation and reasoning, and if we look inside, we can also talk about constraint programming. So it's a kind of a declarative programming, in the sense that if you have a combinatorial problem to solve, like scheduling, planning, and so on, an NP-hard problem to solve, it's possible to tackle it using constraint programming. You can write down the set of constraints that model the problem as a set of variables that take values in a finite domain, and express using relations different constraints that translate the problem into a set of constraints. So once you get the model, you can submit it to a CP solver, what we call a CP solver, constraint programming solver, and the solver will satisfy the constraint, try to find the solution that satisfies all the constraints. So instead of writing down the solution, you can just define through constraint your problem, and the machine will solve it and give to you the solution. This is constraint programming. And the second webinar, we try to see how machine learning can be used in constraint programming, and especially in the step of modeling. So instead of asking the user to write down the constraint, we can just present her or him a set of examples. If we can, if we take the example of a timetabling problem, instead of asking the user to write down the constraint, you can just present some positive and negative examples. And according to the classification that we can get from the user, we learn automatically the constraint. So kind of helping the user to model the problem using constraint. In this third part, we will see the other sense, in the sense that how constraint programming can help machine learning and especially data mining, and how can be used in a particular case. So let's start with the context. So we are in pattern mining, where we have a data set and we have a user that can express some queries through constraint, and this query can be submitted to a specialized miner, in the sense that it's a specialized algorithm that is able to understand the query and to start to enumerate the patterns. So if we are talking about basic queries, we can find in the literature or in different implementations specialized algorithms that are able to enumerate patterns in an efficient way and in a very interesting implementation and algorithmic aspects. But once we get a more sophisticated constraint from the user, expressing some domain-related constraint or some particular properties on the patterns that the user want to extract as a knowledge from the data sets, this can be a complicated task, in the sense that we have three possibilities. The first one is that we try to prepare the dataset using a pre-processing, if it's possible. For example, if the user asks to extract the knowledge in that from a dataset or from something that happened only the weekend, so we can make a projection on the dataset and take only the data from the weekend and make the mining on it. If it's not possible to do a pre-processing, we can try to have a post-processing where we enumerate the patterns, and once we get it, we try to filter out all the ones that violate the constraints and keep only the ones that satisfy the constraints. And if it's combinatorial to do a pre-processing or a post-processing, now the only solution is to think about a new algorithm that solve the sophisticated query that the user express, which can be a very time-consuming task, and not really what we want if we are in a context like interactive data mining process. If the user says something, and once he get the patterns, say more sophisticated things, we need to have an automated process that will adapt the answer and take into account the constraints one after one, without asking the engineers to think about a new algorithm or to do a pre-processing or to think about a post-processing step. So in this context, the declarative programming, like constraint programming, can give an answer to this problem or to this limitation, in the sense that we can propose a CP model that translate the query of the user, and after that we can add, remove the constraint in an easy way and express the thing in a compact way without any difficulty. And we have the generic solution, the generic CP solver, that can take into account any constraint without any problem. And we can produce the patterns in interactive way, or in a process that the query, we start with a query that can evolve during time, something that that is not true at a given moment, or something that need to be reinforced, or something that can be added or must be added to the model. So we are in a context. So here we have the constraint programming, the general framework. We have the problem, combinatorial problem, that we will translate as a set of variables, domains, and constraints. This is what we saw together in our first webinar. And then we will ask the CP solvers to produce the solutions. So in the context of the pattern mining, we have a query, and we will translate this query as a constraint network, variables, domain, and constraint. And we ask the CP miner or the CP solver that will be able to produce the patterns as the solution. So what the first work that tried to use CP for pattern mining, the people were very happy to see that it's very easy to express their mining task using constraints without any difficulties. It's in using different relation constraints and so on, and very in a compact way and very easy way to express the model. But quickly they face the problem of efficiency, in the sense that in terms of expressing the query using constraints, it was a very easy task. But once we submit this to the solver can take time to enumerate all the solution, or to be efficient to response. And this is due to the propagation step. So if I come back to this part, we have the propagation part of the CP solver, which is a kind of algorithm that, given a relation or given a constraint, the algorithm will prune all the inconsistent values from the domain of the variables in an automatic way. It's a kind of deduction that if I have this value and this value, then this value can never be in my domain, so I can remove it without any problem. So asking the CP solver to take into account mining tasks will do the things in a generic way, using the generic algorithm, propagation algorithm. So instead of having a simple model, we can have a model with what we call global constraints. And a global constraint, if you remember, it's a constraint that can be defined and can be proposed with its proper propagator, and that catch a property or something that it's a sub-problem of the whole problem. So if we have this toolbox that we can use in the modeling step and use it in the solving step, we can solve more instances of the problem and be very interesting in terms of resolution. We will take an example on this to see the difference with between the fact that we have a model without global constraints and a model that use global constraints. So the global constraints in CP community, they started to look into more or less the same category of problems, for example, scheduling problems, and they try to find a sub-problem that happen at each time we have a kind of problem that talk about scheduling. And we come out with what we call a global constraint, the cumulative way, one that just catch the properties that the resources and the task can never exceed a given limitation or something like this. And we look into another category of problem, vehicle routing, for instance, and we come out with other global constraints, like all different global constraints say the following things. If you have a set of variables, 3, 4, 5, n variables. Here, the property is that each variable will take a different value. If I have x1 that take the value 5, I will never have another variable that take this value. So in terms of modeling, this part can be used in different problems and so on. So we can, at the end, we have solvers that propose a set of global constraints as a toolbox that in terms of model, we can just express the global constraints. And in terms of resolution or solving, there is a propagation algorithm that is proposed with this global constraint that make the thing easier. Okay, and our aim is to do the same thing for data mining tasks. So looking into mining tasks like item set, association rules, and so on, we started to look into the properties or sub-problems that occur in a frequent way, and to propose global constraints that will make the CP solver efficient in terms of resolution. And we propose a set of global constraints. Here we have more than 6 global constraints, and until now we have more and more people that work in this part to make the resolution more efficient. So let me just take an example to be sure that we understand this part, and we look into what we call the item set mining. The item set mining problem, we have a set of items, okay, and we have a set of transactions, and we talk about transactional databases where you can imagine a customer that at each time go to a given market, will buy some items, and we record all the items that the customer bought. And we have in the definition of the problem what we call a minimum frequency threshold. And the question here is to enumerate the set of item sets that have the frequency that exceed this thresholds. So here we have 10 customers, okay? We have 10 transactions, and in terms of items, we have A, B, C, D, E. Okay, we have 5 items, and we can see that the first customer bought the first item, the item D, and the item E. Okay, and the question here, or the basic query that we can have, is that what are the item sets that are frequent according to a threshold equal to 30%. So this problem is well studied in data mining community, and the idea is to make a search in a lattice. So here we have the lattice where in the top of the lattice you have the empty item set, and in the bottom we have the item set with all the items, and in between you have all the possible item sets of different sizes, and the partial relation here is the inclusion. Okay, and if we want to answer to this question, we need to enumerate all these blue item sets. So if I take the item sets A, E, we can see that in the data set, the item set A, E is a frequent one in the sense that it exceeds 30%. It's appeared in 6 out of 10, and it means that it's an item set that need to be enumerated or returned as a solution. Okay, so there is several algorithm implementations, data structures that are proposed in data mining to enumerate the frequent item sets. So here we have all the item sets, okay? And also there is other questions that are studied in this field, that instead of asking for the frequent, I can ask for some representation or condensed representation of the frequent, some elements that represent all the frequencies. For example, we can ask for the maximal one, maximal in term of size. So a maximal item set is the one that is frequent, and if we add an item, become infrequent. Okay. So once we get the maximal ones, we can deduce or enumerate all the frequencies that are represented with this frontier. Okay. And also we can ask for what we call the frequent closed item set. For given frequency, there is maximal item sets, and the whole set of the different level here or frontiers here represent what we call the closed item sets. Okay. And just to give you an example, here we have some well-known data sets. Okay. If I take the length data set here, we are talking about more or less 10 million frequent item sets. And these 10 million frequent item sets are represented with 46,000 clauses. And these 10 millions are also represented with 5,000 maximal ones. Okay, so the number of frequencies in general is very important exceed in general the size of the data sets. And this is why we look into some representation like the closed and maximal to make more sense about what we want as knowledge that is extracted from the data set. Okay, and in the same way and in a dual manner, we can ask for the infrequent one or the rare item sets, something that happen in the data set with the frequency that is very low. It's very studied in health, for example, domain, where we look into something that happen with the frequency that is very, very low, to check if there is something that we can extract as a knowledge from this. And in the same way, we can, instead of asking for the infrequent way, we can ask for the minimal way, minimal ones, or what we call the generator, which is the dual. The definition is the dual of what we call the closed one. Okay, so this is what in data mining what we call a basic queries. And once the user asks something that is more complicated, like I want something that is okay, frequent, closed, and so on, but also I want to see if there is a correlation between a given category of items and another category of items, or at least two categories of items, or what happened in a time window of 1 hour, to see if there is something to learn. If this kind of constraint is expressed, we have no solution, no specialized algorithm that is able to take into account this question. That is why we do a pre-processing or a post-processing to try to solve the problem. Other way, here in constraint programming, if the user come with new constraint, we have just to put them in the model, and we are sure that what is extracted as pattern is coherent with the set of constraints. Now let us just take a closer look to the first global constraint in item set mining that we proposed to facilitate the resolution and the enumeration of this kind of solution. So the first word that try to use constraint programming for enumerating closed frequent item set mining is the model that we will see together. So here we have this data set with 6 transactions and a set of items. So the solution is encoded with these 2 Boolean vectors. So if I have 1 here, it means that the item set that I will return include the item A. And the fact that I put 1 here, I need to put 1 here, 1 here, and 1 here to say that the item A is present in the transaction number 2, 3, and 4. Okay. If I have 0 here, it means that the one that I'm constructing as a solution is not including the item B, and that's it. Okay. So this is in terms of variables. We have these 2 Boolean vectors, and the domain is 0, 1. And in terms of constraints, we have these 3 package of constraints. The first one is a set of constraints that will say that if I am constructing a pattern, this pattern must be present in a given transaction. So just to be sure that what we will enumerate here is present in a given subset of transaction, what we call the coverage constraint. And these constraints will ensure that what we will produce as a pattern is a frequent one, that the frequency of the item in question exceed the given parameter theta, which is the minimum frequency threshold. And this constraint is about the closeness. It means that what we present at what we give as a solution is one that is closed, that respect the definition of closeness in terms of patterns. So if we look closer to this model, we can observe that we have so the decision variables. So it means that the variables that will be used in terms of decision, and what we are interested in is this variable, this set of variables that encode really what we want to have at the end. And this is what we call the auxiliary variables that will maintain the coverage and can help us to compute the frequency of a given pattern and so on. So the limitation of this model, it's a declarative one. It's easy. It's the first one that uses constraint programming to just model it with these constraints. But the problem is that we have a set of variables that we need to manage. And imagine that your data set is about more than 100,000 transactions. It means that you need to have 100,000 variables, auxiliary variables to handle in the solver. And also these constraints can be very, in terms of memory, can be very, very hard to solver to take them into account, where we have a lot of constraints here that we need to satisfy to return the solution. And that's why, in terms of the resolution, we don't have really interesting results. And we come up with global constraints, but the definition is here. So we just said that the closed pattern, which is a global constraint, maintain the fact that the pattern is frequent and it's closed one. And that's it. This is the definition. And behind this global constraint, we proposed a propagator, an algorithm that maintains this property in an efficient way, and using an algorithm that has a polynomial complexity in terms of time and space complexity. Okay, so let's just see how it works. So the idea is that this propagator will be used at each time we go through the resolution. So for a given, I recall that in a CP solver, we define the search, we will build a tree search, and at a given node, we will just step a moment and say, is there any something, some value that can be removed from a given domain or not? If it's the case, we can remove and reduce the search space. Otherwise, we can go through the resolution and select a new variable, select a new values, and go on, and so on. So if we use this global constraint is based on 3 rules. The first one I will illustrate with examples. The first rule is that if we are in a situation where I have the threshold equal to 3, so it means that here we have 6 transactions, I need to enumerate closed frequent elements that are present at least in 3 transactions. Okay, so imagine that for a given reason in the resolution, we have the variables that encode the item E to 1. So it means that I am trying to construct a solution, an item set with E. Okay, so it means that now I can make a projection and just look into the sub data set where E is present. And E is present in the first transaction, the fourth, the fifth, and the sixth. Okay, and here we have the first rule that can be used. So the first rule say that if we have E, a given item, which is present, and there is something that represents an extension of this item, we can remove the value 0 from this item. So here, if I have E, I will for sure have the item F, because when that on all transactions, at each time we have E, we have also F. And the fact that we need a closed item sets, it means that F is an extension of E. And in this case, we can remove the value 0 from the variables that encode F. So at each time this rule can be used, we apply it and we remove values from domain. The second rule is that it's about the frequency. And imagine that we have here the theta equal to 3, and we are in a situation where we have A, the variable that encode A, to 1. So it means that we will look into these 3 transactions, and the fact that we have theta equal to 3. So here I can deduce that A can never be with B, because if we add B, AB has frequency equal to 0. I never have C for the same reason, because AC, the frequency is equal to 1, and I look for something that is greater than 3. And the same for D, E, F, G, and H. The fact that I put 1 here, the second rule will prune the value 1 from all the remaining variables, saying that if you want solution with A, you can never have the others with A. So the only one that the item sets that include A is the one that include only A in this case. Okay. And the third one is more or less the dual rule of the first one. So if imagine that we have E and F, they have this partial solution with E and F, and we for a given reason we put B to 0. So we are in a situation where we look into this 4 transaction, and if we look into this 4 transaction, we can observe that at each time we have B on this sub data set, we have also G, and vice versa. Okay, so the fact that B is absent, G also must be absent. So it means that I can remove one from the variables that encode G from this dataset, and so on. So this propagator or this algorithm, at each time we make an hypothesis on a variables or we try to construct the solution, several variables can be reduced in terms of domain to reduce the search space and to go quicker to the solutions. So here I just to present some results to see the difference. So here we have the closed pattern, okay, and here we have the CP model that we saw together, just the first declarative model with a lot of constraints and so on. So in terms of time, we can see that here we always have interesting results on the use of this global constraint comparing to the declarative model with a lot of constraint on the coverage, on the frequency, on the closeness. So they say exactly the same thing, but here the fact that we define a propagator dedicated one, we do the things in an efficient way. So in terms of time, so here we have also instances where the model in question is about more 16 gigabyte, and the solver is not able to upload it to solve it. So here we have, instead of having 16 gigabyte, here we have one constraint and the dataset in question, and we can do the things in less than in few seconds. Okay, so this part is the search tree. So we have the search tree, and the fact that we have here less nodes, it means that the search tree is smaller than the one that is explored in this part. And this is due to the propagation. The fact that we propagate more, we remove a lot of values, it means that the search tree is really reduced, and we can, for the same reason, reduce the search space and enumerate the solution in an efficient way. Okay. So yeah, so here just to explain an important point here. So here the comparison with the declarative model, the simple model that proposed by people working on data mining, and this is the one that we proposed to make the CP solver more efficient in terms of resolution. So this is the comparison that we just saw together in the previous slide. And here it's a specialized algorithm, LCM, which is dedicated to enumerate the closed frequent item set. And here we can see that it's very impressive results. It's less than a second, and we enumerate here is the number of closed solutions. So here we have millions of solutions that are enumerated in less than 1 second. Okay, so closed pattern is very interesting, but comparing to the specialized one, we cannot do better than a specialized one, because here we are in a context that we make the things generate, and here we have specialized ones, and that's why they are optimal in terms of algorithmic properties and in implementation. And we will come back to this question after, why we use constraint programming instead of using the specialized one. Maybe I will. Yeah, okay. So this is one of the reasons that we use constraint programming in terms of modeling. There is two answers. The first one is the fact that we have a power, the declarative power that make the use of this technology interesting in terms of modeling and solving. So here, here we have the frontiers that represent the maximals, okay? And we have the other frontiers that represent the minimals. So the maximals, they are frequent item sets that are maximal in size, okay? And the minimals are frequent item sets that are minimal in size, okay? And if we get the frontiers, the maximal ones, we can deduce all the frequent patterns automatically. And if we get, for example, here, all the nodes that are here from ABC and BCDE, we can deduce all the solutions that are here. And in the same way, here we have, according to this border, we have the infrequent or rare item sets. And from these two elements, we can deduce all the solutions. And people working in data mining, in particular in pattern mining, they define solutions that try to enumerate the maximals, or other solutions that try to enumerate the minimals. And using CP or using constraint programming, we can enumerate the minimal or the maximal or both in the same way, in an easy way, without any thinking about an algorithm that is dedicated for this task or this task. And here, just we can analyze together the question. So the maximal, we have two properties, A and B. A, the fact that it's frequent. B, it's the fact that a maximal a maximal item set has only frequent subsets. If you take an item set that is maximal, all the subsets are frequent elements. So if you take ABC, all the subsets are frequent. The subset of ABC, AB, for example, it's infrequent. AC, it's frequent. B, it's frequent. A, also. C, it's also the case. And in terms of minimals, the minimals ones, they are infrequent one, but the red part here, they don't respect the frequency constraint, and they have only infrequent supersets. It means that if you take AD, for example, AD is minimal ones, and all supersets are infrequent ones. You construct any item set from AD, you add something to AD, you can go to one of the elements that are here. So from this, we can, if we want to enumerate the maximals and the minimals in the same time, so having a solution that enumerates these two nodes, the blue nodes and the red nodes at the same time, we can just try to satisfy this property B and this property C without looking to the frequency. And if we get this, if I want only the maximals, I can add the property A. If I want only the minimals, I can add the negation of the property A, and that's it. So, and this can be expressed in very easy way in constraint programming. So in constraint programming, you can just have this model saying that we have a global constraint here that say that this global constraint say the following things: enumerate the pattern that have only frequent subset. Enumerate the patterns that have only infrequent supersets. So two global constraints, okay, that encode the property B and the property C. And then you can add a reified global constraints, saying that if you want the maximal, you put B to 1 and you get the frequent. If you want the minimal ones, you put B to 0 or to false and you get the minimals. And this is from this model, okay? So this is the power of CP in terms of modeling and in terms of writing down the different models. And let's go to the association rules to show the efficiency of in terms of solutions. So the association rules here. The association rules. So it's a kind of implication. We have the body of a rule and the head of the rule, the X that imply Y. And we can say that at each time we have this, we have also this. And this rule have a given confidence. This rule is true with a confidence equal to 70%, or this rule is valid to a given threshold. So we talk about the body and the head of the rule, and the fact that there is no item that are shared between the body and the rule and the head of the rule. For example, here we have a data set, and we can say that at each time we have E and F, we have also B, and this rule is valid for with a frequency that is equal to 50%. It's true in 50% of the data set. And in terms of confidence of the rule, this is the definition of what we call the confidence of a rule. And this is true. This is true at 75% in the data set. Okay, so this is the basic definition of the problem. And in the same way, we propose a CP model that is able to enumerate the association rules. We have a Boolean vector for the body of the rule. Here we have the vector Boolean for the head of the rule that encode the head of the rule. And Z here, or Z, it's a vector that represents the X union Y in terms of items. So the fact that we don't want to have items that are shared between X and Y, it can be expressed in an easy constraint here, like saying that if I have for a given item, if I have X to 1, I cannot have the corresponding Y to 1, and that's it. Here, it's just to say that I don't want rules with an empty head. Here, it's just to make the link or a channeling constraint between X, Y, and Z, saying that here we have the union. And once we have this part that define the problem, we can add the frequency, saying that the rule must be frequent. So saying that the rule must be frequent, we can put the constraint, and that's it on Z. And the rule must be confident, and here we define a global constraint for the confidence. We add the X and Y, and that's it. Here, just what you want, what you have to write in your model, you submit it to the solver, and the solver will enumerate the solution. So, yeah, I have 2 minutes, I think. Let me just go to the slide where we show some solutions. So imagine that we need to enumerate the association rules. Okay, so here we have a specialized algorithm that is able to enumerate the solution, the rules in a really efficient way. So example here, for this data set, we enumerate more than 30 million solutions in less than 25 seconds. In CP, with the model that I presented to you, we need more than 40 seconds to enumerate it. However, what can we observe here is for this instance where both are reaching the timeout. So here we reach the timeout of 1 hour without any solution that is proposed. Because if we look into the specialized algorithm, it started by producing the body of the rule, producing the head of the rule, and make a matching between these two sets. So it spends more than 1 hour just by producing the X and the Y without making any link between them. That's why after 1 hour, we have zero solution that is produced. In terms of CP, we can start enumerating the solution one after the second one. And here we reach more than 390 million solution before the timeout. And the first solution is enumerated in less than 1 second, in 2 seconds. Okay, but in the context where we need to enumerate the association rules, simple question, the specialized one is the faster one, and we need to use it. But if we have a complex query that the user say, I want rules that have this particularity in the body, this particularity in the head, no sharing between these two subsets and so on, we can use the specialized one, but we need a post-processing step, okay? In terms of CP, we can add only the constraint to the model that I presented before. We add the new constraint, and that's it. So here, for example, one of the query, the user asks something, and the CP in less than 1 second can return the 12 solutions. But in terms of a specialized one, he will start by enumerating the 30 million and then filter out all the no solution to keep only the 12 solution. Another interesting point is that here we have zero solution to what the user is asking for. And in less than 6 seconds, the CP model can detect it, saying that there is no solution to your problem. But for using the specialized one, we need to enumerate the 1 million solution and then filter out all the solution to say at the end, no one satisfy what remain as constraint. Okay? Yeah, I can stop here if there is any question, and thank you.
You can conclude, Professor Nadjib.
Yeah, okay, thank you. So here, just the takeaway message. So the main thing that we need to keep in mind is that if we are looking for enumerating the patterns, there is no complicated query to use and so on. So here, the choice is to use the specialized algorithm. They are dedicated for. That's why we use them. But if we are in a context where the user can say something and add something else and propose something like in interactive exchange with the user, this can motivate the use of constraint programming in terms of modeling, saying that whatever the user will say, I can express it in terms of constraint and add it to my model. And also, I have the guarantee that I can be efficient with what the solver proposed as global constraints. So some open question, and the people that are working on is to try to have something hybrid, in the sense that an intelligent miner that can start with something that is specialized algorithm, and once the miner has difficulties to take into account constraint, can go to the declarative model and try to solve it in an adaptive way without asking the user to manage the things or something like this.
Thank you so much, Professor.
You're welcome.
And now we pass to the questions asked by our guests. We start. I will read the questions in the same order as they have been written. The first one is given by Fatih bin Khalfallah. The question says, please, what types of patterns can be extracted using the data meaning features?
So here we make the choice to take the example of the simple one, which is item sets. We have the transaction or the items are represented using sets, and we can extract the knowledge in terms of item sets. So the structure here are represented with sets, but we have exactly the same work or more or less more proposition for sequence mining, for example, that we have the element that can are put it in a given order, and the repetition is allowed. And also we can have a mining on graphs and or trees or something like this, and exactly the same conclusion and observation that we have here in this talk are true on the other mining task, in the sense that specialized algorithms exist. A lot of specialized algorithms exist for different structure, for different mining tasks. And for CP, we have more and more works that propose this declarative approach to enumerate the patterns.
The second question comes from Amina Aliji, and she says, how do constraints impact the scalability of data meaning methods?
So, how the constraint
impact the scalability
of So this is a very good question, where we this is the motivation that that push us to look into the global constraint, because the scalability with the use of elementary constraints, saying that I have a mining task and I will write down the constraint, and at the end I find myself with a huge number of constraints to model the task. So in this case, we can face a problem of scalability, in terms that in this particular task, we need an important number of constraints, which means that in terms of space, it can be very hard to solve. And that's, if we reach this point, this can push us to look for global constraints, saying that, okay, there is a lot of constraints. Now, is it possible to catch the semantic of all these constraints to be represented by one global constraint that can express exactly the same thing and having an efficient propagator behind? So the scalability here, it's a question that now data mining people that look for constraint programming are taking into account, using global constraints as a solution.
Thank you so much. The next question from the same person, Amina, and the question is, what's the impact of combining border and constraint-based approach on the quality of patterns?
So what is that? Okay, so the notion of quality, I don't really see what does it mean exactly, because now we have we are facing some queries that look for patterns. So now if we prefer something then another one, or there is a quality of the pattern in terms of some objective function that we express, we are in a context where we can differentiate the patterns, and this can be expressed with the dominance constraints that can be expressed in the model, saying that, yeah, okay, I get this one, but I now, according to the dominance constraint, is there any solution that is better than this one? And we can go through this. But maybe the question is linked to the fact that we have anti-monotone constraints, about the closeness or the maximal properties, and the fact that we have other constraints that can interfere with this constraint, in the sense that for a given question we can have two interpretations. And in this case, we have a paper on this question that explain that at a given question we go from NP-hard problems to another category of problems, which is a co-NP-hard problem, where we need to solve a sequence of CP models to get the really the right solution that we look at. So just to be clear, we ask for maximals that have a given properties. So these given properties, so we can do the things in two different ways. Maybe we can start by enumerating all the maximals, and after that keeping only the ones that satisfy the new properties, or enumerate all the frequent patterns that satisfies this property, and after that we compute the maximality about these patterns. And these two different interpretation, it's due to the fact that constraints that we will add can interfere with the constraints that are anti-monotonic ones.
The next question from Salah, and he's saying, what are enhanced patterns mined in data mining?
So here it's maybe I think it's about the title, and the idea here is that the mining community now is looking more and more to the question that there is the human in the loop, and we need to have methods and approaches that can be adaptive and can understand what the user wants and can respond in real time without the need to propose a new solution and so on. So in interactive data mining or user-centered approaches, so now people work more and more to this question, and all of them agree with the fact that we need declarative approaches to be efficient in terms of mining patterns.
Okay. The next question from Amina. How do border-based method complement and enhance the capability of advanced machine learning algorithms?
So I don't know if here the border-based methods about CP or not, or what we discussed it just before.
We can pass to the next question, and you ask Amina to send you direct to the question, and maybe answer her directly. The next two, or the last two questions, the amount of data we are dealing with, does it affect performance of algorithm, for example, big data case? This question by Zelina.
Yes. Of course. This is the main factor here is about the data set size. So here we express the complexity in terms of number of items and number of transactions, and the fact that we have complexities that are polynomial engineered on the size of the data set. It's a good news. That means that we can do the things in a polynomial time without any problem. The idea is to be able to upload the data set and to work on it. So if it's possible to work on a big data case with a specialized algorithm, there is no reason why the CP models cannot be the same with the same data set.
Okay, thank you. The last question by our guests comes from Bilhassan, and he's saying, how does the enhanced pattern miner address limitations such as high dimensionality or concept drift in data?
So, so this kind of if I'm not wrong about the definition of this what you call limitation of these problems, I think that the idea of CP and the fact that we can add constraints and revise them and modify them, we can come up with an approach that is able to start with a CP model, and during the resolutions, if there is something to take into account in terms of dimensionality or concept drift, we can revise the model by replacing some constraints or adding a new one and restart the resolution to enumerate the new solutions.
Thank you, Professor Najib. If you allow me, I have some mathematical questions. If I well understood what you did or what you presented. So on page 13, when you define the maximality, in mathematical point of view, when we say or define maximality concept, this means that there is some order, isn't it? There is some order which is maybe inclusion, I think, between sets.
Yeah, so here we have the partial order.
Yeah, so my question is the sensitivity of all what you did relatively to the order. If we define, I mean, if we use another order, you know that we can take different or various orders between sets. What would happen if we change the order that you have used?
So you mean that if I start with something that reorder this lattice and the element that compose this lattice in a different way, what is the impact on it, right? Right?
Yeah, I give you an example. For example,
Yes.
for vectors, we can say that the vector is less than or equal the second one. If, for example, all the components are strictly less than all the components of the second one, we can take another order. We work only with one component, and all the orders should be equal. And many other orders that you can define. My question is the sensitivity in some sense if we change the order in your framework.
So if we change the order, we now so we are changing something essential in the definition of the problem. It means that also the specialized algorithm will not be able to take another definition of the order between the item sets. They go from the fact that we have the inclusion between the elements, and this is a property that is used in the algorithm to facilitate the propagation, saying that if I have a frequent item set, all the subsets are frequent. So based on this relation. And also if I have an infrequent item set, all the extensions are also infrequent, and they prune the search space based on this order and on this solution on this property. And we do the same also in the propagator and in CP model. Now, if there is another definition of the order between the elements, we need to think about how the propagation will occur and how we can deal with this new reorganization of the items, and it cannot be straightforward, for sure.
The second one, if you allow me, is or concerns what you call the closed, I think, closed items or closed sets.
Yes.
If I understood what you gave is in some sense is an equivalence class. You take or you choose some elements of your big or huge set as a representative. When we say equivalence class, this means some relation of between, let's say, uh, equivalence relationship between elements. The same question, the sensitivity, if we change this equivalence class. I mean, instead of taking this or that point, of course, accordingly to some relation, we take others, of course, accordingly to another equivalence class.
Yes. So the equivalence here, or it's a class of elements that are represented by an element. So it's not really an equivalence one. In equivalence class, it means that whatever the point that I will take from this class will represent all the class. Now here it's an element that can represent a class. It's a really condensed representation. But the fact that we have different classes and all classes are represented with closed one is expressed with the constraints here. Now, if there is something else or the different way to express it, if we can rewrite it in a mathematical way, and this new equivalence, we need to replace it and to rewrite this part with the new one. So it's the sense here for sure. We need to be sure that the way that we define the variables, the domains, and the other constraints are coherent with this new definition. It cannot be straightforward again.
Okay, thank you so much, Professor Nadjib, for your nice and very interesting presentation. And we have also to thank all the guests for their pertinent questions. And I think it's time to close our webinar and the series of webinars by Professor Nadjib. And we have to thank him a lot. And see you, inshallah, on the next WAST webinar. I don't know the title, but inshallah, see you next time. Assalamu alaikum wa rahmatullahi ta'ala.
Thank you very much, Nadjib. Thank you very much for everyone.
Thank you, Faiz.
Thank you. And yeah, we hope to see you, inshallah, next year. But yeah, that was great. Thank you. Thank you so much. Thanks. Thank you all.